So now we're going to talk about how to compute the Fibonacci series. It seems like a very simple process. You learned about Fibonacci in grade school. But it turns out that if you try to use a naive strategy for computing the Fibonacci numbers, you end up getting an exponential time algorithm, which is not good. We can get a linear time algorithm. That means to compute the n Fibonacci number runs on the order of n time using a slightly smarter dynamic programming trick. We'll see how that works. So now let's think about how to compute the Fibonacci numbers. Just to remember, the Fibonacci numbers start as 0, 1, 1, 2, 3, 5, 8, 13, and so forth. But as you probably recall, the way you define the Fibonacci numbers is f of 0 is 0, f of 1 is 1, and then for any larger n, f of n equals f of n minus 1 plus f of n minus 2. Right? That's the standard definition of Fibonacci numbers. You just add up the last two terms to get the nth term. Now what we're going to do is define some pseudocode that computes the Fibonacci numbers using one attempt. I'm actually not going to use pseudocode. I'm going to use Python. It's my favorite pseudocode. Okay, here's my pseudocode. Notice the first line, it checks if n is equal to 0, one of the base cases, in which case it just returns 0. Then it checks if n equals 1, and then in which case it returns 1. Otherwise, it's going to return fib of n minus 1 plus fib 1 of n minus 2. Notice it makes two recursive calls to fib 1 to compute this, right? And it's very natural given the above formula that we would do this. Let's now think about how to compute the running time of fib1. By running time, we generally mean like the number of steps the algorithm takes. And of course, a step isn't always super well defined because you have different machine architectures, but typically we mean a unit operation of the computer. So now let's let t of n be the running time of computing the n Fibonacci numbers using this fib1 operation. We'll notice that t of 0, it takes about one step, right? Because if you think about this algorithm, computing t of 0 requires checking is n equal to 0, that will return true, and then we'll return the number 0. That takes about one step. We could say on the order of one step, but let's just say it takes one step. T of 1 equals 2 steps, right? Because when you input 1, first you have to check if n equals 0, then you return 0. Then you check if n equals 1, that returns true, and then so you return 1. So it takes about 2 steps, right? And so for n bigger than 1, t of n actually equals t of n minus 1 plus t of n minus 2 plus, let's say, 3. Now, where am I getting 3 from? Well, notice that it has to do this operation here, it has to do this operation here, and then it has to compute fib1 of n minus 1, which is where this t of n is coming from. T of n minus 1 is coming from, right? This guy right here is coming from this call. This t of n minus 2 is coming from this call, right? And the 3 here comes from the fact that we have one operation we check first, another operation, and then we have to add these two terms together, and that's a third operation. I'm going to call that a step of the algorithm. So this is my formula, roughly speaking. This is a decent formula for an estimate of the running time of fib1. Okay, now let's dive deeper into this running time calculation, t of n. Recall that, so as I just wrote in the last slide, t of 0 equals 1, t of 1 equals, this should be 2, and t of n equals 3 plus t of n minus 1 plus t of n minus 2. Now, the question is, how big does this grow as n gets large? That's the question we want to answer now. So one thing you'll notice is that this looks a little bit familiar. It looks similar to what when we actually computed the actual Fibonacci sequence. The actual Fibonacci sequence, if you remember, we said f of 0 equals 0, f of 1 equals 1, and f of n equals f of n minus 1 plus f of n minus 2. Now, I'm going to make a claim. The claim is that t of n is always bigger than f of n, right? Just given these two expressions. Now, why is that? Well, I guess this can be proven using induction. So I'll just write proof is an exercise. Just have to check kind of the base case and then the recursive step. But the key thing here, key thing to note is that you'll notice that T of n looks very similar to this f of n recursive expression, except that T of n has this 3 here, right? So it definitely is getting larger. Not only does you adding the last 2 terms, but you're getting larger with that 3. So we know that T of n is going to be larger than f of n, right? And in fact, we can also, if you want to, we can also write that T of n equals omega of f of n, if you like. So how fast does f of n grow? Well, you might not know this, but it turns out that we know that asymptotically, so for large n, f of n is roughly, we call phi to the n all over the square root of 5. What's phi? Phi is the golden ratio. You can look up the golden ratio if you like on your own time. It's an interesting quantity, comes up all over the place. Of course, it's defined as the square root of 5 plus 1 all over 2, right? But the key thing here is that f grows, I should write roughly, this isn't exact. Roughly, it'll asymptotically converge to that quantity, but it grows exponentially, and we don't have to talk about here why that's the case, but just believe me that f of n grows exponentially. So if f of n grows exponentially, that means that t of n also grows exponentially, because t of n is growing more quickly than f of n, or at least it's larger than f of n, right? So running time of fib1 is thus exponential in n, right? Which is bad, which is a bad thing. That seems a little bit funny, right? Exponential growth can get obviously very large. It seemed when I was calculating this before on the paper that wasn't what was happening, that the time it took me to compute the nth Fibonacci number seemed to be linear in the number of steps. So what's going on here? Somehow there's a bug, right? There's some kind of a bug going on here. So let's talk about what the challenge is. The issue here, of course, is that in order to compute fib1 of n, right, I had to compute fib1 of n minus 1 and fib1 of n minus 2, right? I had to go and do these subtasks recursively, right? Now, let's think about how this tree continues. So now notice that to compute fib1 of m, if you look down the tree of recursive calls that we had to do, you'll notice a lot of repetition. For example, look, fib1 of n minus 4, just how I've drawn it. There's 1, 2, 3, it's over here, 4, 5, and there's actually more calls as well, right? So I was repeating the call to fib1 of n minus 4 multiple times. I computed that multiple times. I didn't need to do that, right? I can record that computation and save it for later when I need to access it again. So this recursion is blowing up in ways that it doesn't need to. We can be a little bit smarter about how we compute this thing. Okay, so now let's try another method using what's called dynamic programming. Dynamic programming is an algorithmic strategy for solving a big problem by reducing it to smaller subproblems, especially where the subproblems overlap with each other, so you can remember having solved other subproblems, kind of like our recomputation of t of n minus 4. So let's look at let's write some pseudocode for this new strategy, and we're going to call it fib2. I'm going to use my favorite pseudocode, which is Python. Okay, so the first thing that fib2 is going to do is it's going to first check if n is 0 or 1, just using some Python shorthand here, and then it's going to return n, obviously, because f of n is for the first and second Fibonacci number, the 0th and first, or Fibonacci sequence is just the index, right, 0 and 1. Then it's going to create this blank array, right? It's going to create a blank array. This isn't Python code. Blank array is not a Python term, but let's just say I can initialize an array of size n plus 1. Okay, so the first thing we do is we initialize the array with the first 2 Fibonacci numbers, 0 and 1. And the next thing we do is this iterative procedure where we start from I going from 2 to n plus 1. and we fill in the value of I is the value of f at I is the value of f at I minus 1 and the value of f at I minus 2. And of course, you're guaranteed to have already completed these quantities, right? Because you already computed the Fibonacci series up to, but not including the previous I, right? You already did it for 1, 2, up to I minus 1. So these things will already be filled in. And you'll notice the way that we've done this here, you won't actually repeat computation of, let's say, f of I minus 2. You won't have to recompute this. This isn't making a recursive call. It's looking up the value that was already computed in this array. The last thing we do is just return f of n, and that's the output. Okay, now we need to think about how to compute the running time of this algorithm, the number of steps it takes. Okay, so the first line of this algorithm is an O of 1 operation. It takes O of 1 operations, right? A constant number of operations. It has to check if n is 0 or 1. Otherwise, it returns n, if that holds true, right? But if n is bigger than 1, then it has to initialize this blank array. There's a question about what data structure you're going to use to initialize this array. It can take O of 1 time. It can take O of n time. Let's just give a rough upper bound. We'll say this takes O of n time. O of n operations to initialize an array. Let's say it does it the slow way. Okay, the next line in this code is to just initialize the first two values. Again, this takes O of 1 operations, O of 1 steps, right? Because it just has to fill in two values in the array. Nothing scaling with n here. And then we have, you have to do a loop that has roughly, I think it's n minus 1 iterations of this O of 1 operation, right? The O of 1 operation is looking up the previous two values, adding it together, and then filling that into the ith value of the array. It has to do that n minus 1 times an O of 1 operation. Therefore, in total, right, this takes O of n time, right? O of n minus 1, O of n minus 1 is also O of n, right? And this, of course, is an O of 1 operation. So in total, we have an O of 1 plus an O of n plus an O of 1 plus an O of n plus an O of 1. That's still on the order of n, right? This is just O of n. The running time of this algorithm is linear in n. The key takeaway here is that the recursive strategy fib1, it seemed very nice and simple, but it has a computational blowup, exponential blowup in the running time because it doesn't efficiently use computation in the right way. This dynamic programming solution, which tries to reduce the problem of computing the nth Fibonacci number to previously solved subproblems and then solve them iteratively one by one, that's what we call generally dynamic programming, is much more efficient and is a linear time strategy for computing the nth Fibonacci number.